So next is equation number 7 and 8 we have to use to derive the equation of reflection coefficient and transmission coefficient. So let's define the reflection coefficient. Reflection coefficient is defined as ratio of reflected wave to the incident wave. So because we are defining it for the parallel polarization, from equation number 7, I don't have this equation, you can refer that. The reflected wave is represented by ER0 and the incident wave is EI0. So according to that, I think it should be 1 plus gamma parallel equal to cos theta t divided by cos theta I. It should be the equation number 7, and the transmission coefficient, this is the reflection coefficient, and similarly if we define the transmission coefficient, then the transmission coefficient is the transmitted wave divided by incident wave, and that would be ET0 divided by EI0, and it is tau parallel. So this was equation number 7, okay. And from equation number 8, you can refer that. Actually I don't have that equation, but I can recall it. So that equation is 1 minus gamma parallel, this is for the parallel polarization, and it is equal to eta 1 divided by eta 2 is multiplied with tau parallel. So these are the two equations which we are getting. So tau parallel, I am writing it here separately. This tau parallel is nothing but ET0 divided by EI0. This tau parallel is ET0 divided by EI0. So according to that, I had written this equation number 7 and 8. Now we have to use this equation number 7 and 8 to derive the equation of transmission coefficient and reflection coefficient. So let's take addition of these two equations. As you can see that this is 1 plus gamma parallel, this is 1 minus gamma parallel, and when we add these two, this gamma parallel will get cancelled. So adding these two equations, I will get 2 equal to, because this 2 will get cancelled and we get 2 equal to cos theta t divided by cos theta I plus eta 1 divided by eta 2, and the tau parallel is common. So if I take the LCM, this is eta 2 cos theta I is eta 2 cos theta t plus eta 1 cos theta I. This is multiplied with tau parallel. So the value of tau parallel is 2 times eta 2 cos theta I divided by eta 2 cos theta t plus eta 1 cos theta I. This is the transmission coefficient. Let me check once the formula for that. Yes. So 2 eta 2 cos theta is equal to eta 2 cos theta t plus eta 1 cos theta I. So the second medium associated angle is second angle, that is the transmitted angle. The first medium associated angle is angle of incidence, this is the theta I. So eta 2 eta 1, and when in the transmission coefficient, if in the numerator it is eta 2, but the angle of incidence we have to consider. So the second medium and the first angle. So you can relate and you can remember this formula. So if I substitute the value of tau parallel in this equation that we got from the equation number 8, we can have the equation of the reflection coefficient as well. So the equation of reflection coefficient, 1 minus gamma parallel equal to eta 1 divided by eta 2 tau parallel, which is 2 eta 2 cos theta I divided by eta 2 cos theta t plus eta 1 cos theta I. So this eta 2 and eta 2 will get cancelled, and the gamma parallel is 1 minus this one. So gamma parallel is 1 minus this whole term, which is 2 eta 1 cos theta I divided by eta 2 cos theta t plus eta 1 cos theta I. So when we take the LCM, we will get gamma parallel equal to, this is eta 2 cos theta t plus eta 1 cos theta I minus 2 eta 1 cos theta I divided by eta 2 cos theta t minus plus eta 1 cos theta I. So this is eta 1 cos theta I, this is 2 eta 1 cos theta I. So after taking the difference, we get gamma parallel is equal to eta 2 cos theta t minus eta 1 cos theta I divided by eta 2 cos theta t plus eta 1 cos I. So this is the formula of reflection coefficient for parallel polarized wave. So this is the for the parallel polarized wave. So now we have got the transmission coefficient and the reflection coefficient. Now we will define Brewster angle. Okay, so you can take a pause of here because the derivation was long. So the derivation was long, and how do we write the equation that you can see? By the diagram of the oblique incidence, we can easily write the equation. So whenever the diagram of the oblique incidence is given, resolve the propagation vector, resolve the electric field, and according to that write the equation. And if you want to calculate the reflected wave peak value, this is the reflected wave peak value, that is you have to multiply with the reflection coefficient. If you want to calculate the transmitted wave peak value, you have to multiply it with the transmission coefficient. It tells us how much portion of the wave that is transmitted and how much portion of the wave is reflected. It is determined with the help of transmission coefficient and the reflection coefficient respectively. So when we wrote the equation of the transmitted wave and the reflected wave, we consider the peak value. So in the question, it is given that the incident electric field, every time when you see the question, it is incident electric field will be given to you, and according to that incident electric field you can calculate the other components, or if the incident electric field is not given, then the figure is given to you. According to that you can write the incident wave equation and also for the reflected wave and transmitted wave according to the diagram. So next is Brewster angle. So Brewster angle is the angle of incidence for which reflection coefficient is 0. The angle of incidence for which reflection coefficient is 0 is called Brewster angle. Reflection coefficient is 0 is called Brewster angle. That is, if this theta I become theta B parallel, that is for parallel polarization we are defining. So the angle of incidence is Brewster angle, then gamma parallel would be 0. When the angle of incidence is equal to the Brewster angle, then the reflection coefficient is 0, or you can say that the reflection coefficient is 0, then the corresponding angle of incidence is Brewster angle. So the gamma parallel will be 0, the gamma parallel will be 0 when the numerator will be 0. So this numerator will be 0 when eta 2 cos theta t is equal to eta 1 cos theta I, and theta I is equal to how much? Theta B parallel. When this condition is satisfied, then the gamma is equal to 0. This is the angle of incidence for which reflection is 0. Now, we can we can derive the equation of theta b parallel when we write all the equation of eta 2 mu naught mu upon epsilon, here also mu by epsilon, and theta t in terms of beta 1 sin theta I. Then we will calculate this whole part, then we at the end we will get sin theta b parallel, or you can directly write sin theta b is equal to sin inverse root over, because the derivation is not important, so I am not deriving it here. This is 1 minus mu 2 upon mu 1 epsilon 1 upon epsilon 2 divided by 1 minus epsilon 1 divided by epsilon 2 whole square. This is the formula of Brewster angle. If you want to calculate the Brewster angle, then you can have this formula. You can apply it directly in this equation, the values, and you will get the Brewster angle. Now, if both the medium are lossless, as we have considered, or instead of writing if, this since both the mediums are lossless, we can write this theta b parallel equal to sin inverse root over, this is 1 minus mu naught into mu r2 epsilon naught into epsilon r2 1 epsilon r1 and mu naught mu r1 and epsilon naught epsilon r2 divided by 1 minus epsilon naught epsilon r1 divided by epsilon naught epsilon r2 whole square. Then this epsilon naught mu naught epsilon naught will get cancelled, and this epsilon naught is also cancelled, and since both the medium are lossless and non-magnetic, let us say, and non-magnetic, and if they are non-magnetic, then mu r1 equal to mu r2 equal to 1. So, in the next step I will consider this. This is sin inverse root over 1 minus epsilon r1 divided by epsilon r2 divided by 1 minus epsilon r1 divided by epsilon r2 whole square. So, this is a square minus b square. So, if I apply the formula a square minus b square, that is a minus b and a plus b, then we get sin inverse of root over 1 minus epsilon r1 divided by epsilon r2 and whole divided by a minus b and a plus b, a square minus b square, a plus b and a minus b. So, a plus b and a minus b. So, this will be cancelled and we get sin inverse of root over epsilon r2 divided by epsilon r1 plus epsilon r2. So, this is in very simple form. The formula here is consider that if the both medium are not a non-magnetic, then you have to follow this formula, but if the both medium are lossless and non-magnetic, then the result is very simple, that is epsilon r2 upon epsilon r1 plus epsilon r2, and that is in the form of sine. So, if I write it, because this is a sine, so if I represent this in the form of sine, in the right angle triangle, this would be epsilon r2 and this would be epsilon r1 plus epsilon r2, because sin theta b is equal to height upon hypotenuse. So, height upon hypotenuse, yeah. So, what would be this value? So, this value would be epsilon r1, because it is square minus this is square. So, this will be epsilon r1. If you square it, you will get epsilon r1 plus epsilon r2 minus, if you square it, epsilon r2 will get cancelled and you will get epsilon r1. Hence, if I want to write tan theta b parallel, that is the Brewster angle for the parallel polarization, the tan theta b parallel from this right angle triangle from this right angle triangle, this is the 90 degree, the tan theta b is height divided by base, and height is root over epsilon r2 divided by epsilon r1. So this is the formula that you have to remember for non-magnetic medium. If both the mediums are non-magnetic in nature, then you can calculate directly tan theta b parallel, which is Brewster angle, that is the root over the permittivity of the second medium to the first medium. And since the wave is travelling from 1 to 2, the ratio of permittivity is 2 to 1. So because the wave was travelling from medium 1 to medium 2, that's why the Brewster angle is root over epsilon r2 divided by epsilon r1. If the wave is travelling to region 2 to region 1, medium 2 to medium 1, then the Brewster angle will become root over epsilon r1 divided by epsilon r2. If wave is travelling from medium 2 to medium 1, theta b parallel will be tan inverse final medium minus initial medium, medium 2 to medium 1 divided by medium 2. This would be the Brewster angle. Wave is travelling from medium 2 to medium 1, so it is travelling 2 to 1, so ratio will be 1 to 2, ratio will be 1 to 2. And here wave is travelling from medium 1 to 2. So this will be 2 to 1, so ratio will be 2 to 1. So this is all about the reflection coefficient, transmission coefficient and the Brewster angle. Now we will see the importance of Brewster angle. Next is importance of Brewster angle. So I am telling you a few points and please note it down, and I am writing it on the board also. So you can note it down and then we will discuss about these points. So the first point is, it shows that by proper choice of angle of incidence, the reflection from any material for a parallel polarized wave can be cancelled. So you can note it down. We are saying that it shows that if you have a material, any material, and if you select the angle of incidence equal to the Brewster angle, then you can make the reflection 0. So here it is written that it shows that by proper choice of angle of incidence, the reflection from any material, this is any material, but you have to select the angle of incidence equal to the Brewster angle, and that can be calculated with the help of root over epsilon r2 divided by epsilon r1. So if you are having the two material and you can have the permittivity of those material, because for each material the permittivity is fixed. So according to that you will get the Brewster angle, and by that angle you incident the wave, parallel polarized wave, then there will be no reflection, all the wave will be transmitted. So this is the importance of this first point. Now the second point is, if a wave has electric field intensity which has components parallel and perpendicular, perpendicular to the plane of incidence. If a wave has electric field intensity which has components parallel and perpendicular to the plane of incidence, and if wave incident on a material interface, if wave incident on a material interface at Brewster angle, this is a very important point, at Brewster angle, the reflection of parallel polarized component is cancelled. Parallel polarized component is cancelled, but not that of the perpendicular polarized, The reflected wave consists of perpendicular polarized component. This is the second point, and let us talk about this. So, here we are saying that suppose this is the interface, z equal to 0 and x and z. Now, the wave is incident from here like this, and this wave is having the two components. Any electric field is having both the components, parallel component plus perpendicular component, can be written in sum of these two, parallel plus perpendicular, and this wave is incident. Okay. So, when the wave is reflected, if the angle of incidence is this theta I is equal to theta b parallel. So, what will happen when the angle of incidence equal to Brewster angle, then we know that there will be no reflected wave in case of parallel polarized wave, because when the angle of incidence becomes the Brewster angle, then the reflection coefficient becomes 0, and here the reflection coefficient is 0. So, if the reflection coefficient is 0, then ER0 is also 0. That means there will be no reflected wave for parallel polarized wave. So, there will be no reflected wave for parallel polarized wave. But if there is wave existing, that means if there is a wave, then this wave has to be perpendicularly polarized. Because I am drawing the wave here, that means this wave is existing because the parallel polarized wave is not cancelled, because the parallel polarization, when we study, we will see that the Brewster angle is different from the Brewster angle which we have calculated in case of parallel polarization. In case of parallel polarization, this Brewster angle is tan inverse of root over epsilon r2 divided by epsilon r1, but when we define for the perpendicularly polarized wave, we will see that it is different. So, we cannot have a single angle of incidence for which both reflection coefficient is 0, that is for parallel and perpendicular. We are having one angle right now which is known as Brewster angle, and for which the reflection is 0. So, the parallel polarized wave will be cancelled. So, the reflected parallel polarized wave will be cancelled, and if there is a wave still present in the reflected wave, so that has to be a perpendicular polarized wave. So that was written here. So if the plane of incidence, if the wave incident on a material interface at the Brewster angle, the reflection of parallel polarized component is cancelled because reflection coefficient is 0, but not that of the perpendicular polarized, because the angle of incidence is not equal to the Brewster angle for perpendicular polarized. So if there is a wave existing, so that has to be perpendicularly polarized. This is our second point, and that is also important point. Now we are having the last point. For any general wave, polarized or unpolarized, the reflected wave will be linearly perpendicularly polarized to the plane of incidence if angle of incidence is Brewster angle. What we are saying is that if the wave is incidenting on a material interface, and if the whether it is a polarized or unpolarized, if the reflected wave is present, then that reflected wave will definitely be linearly polarized. As I told you that if this wave is incident with the angle of incidence equal to Brewster angle, if it is z axis and this is x axis, if angle of incidence is equal to theta b parallel, and this wave is a polarized or unpolarized, it does not matter. So it is whether it is polarized or unpolarized, if this angle of incidence is equal to theta b parallel and the wave is still present, so that has to be linearly polarized, and this is because of the perpendicularly polarized wave. The perpendicular polarized wave is always a linearly polarized wave. So this is a linearly polarized. If the wave incident is whether it is a polarized or unpolarized, the reflected wave will always be linearly polarized. Or you can say that if it is given to you that the reflected wave is linearly polarized, then you can assume that the angle of incidence is equal to the Brewster angle. So if reflected wave is given as linearly polarized wave, then take angle of incidence equal to Brewster angle. Okay, and if the reflected wave is 0, then also take theta I is equal to theta b parallel for parallel polarized wave. That we have already considered, just I am writing these two form in separately, but this second point we have already seen that the reflection coefficient will be 0 for angle of incidence equal to the Brewster angle, and this part is new, and this part is nothing but the conclusion of this third point in the opposite manner, that if the reflected wave is linearly polarized, then the angle of incidence should be equal to the Brewster angle. So this is all about the importance of Brewster angle that you have to consider, and this is very important because many times the gate has been asked the question from this topic. So you have to always take care of this, the importance of this particular Brewster angle, and how do we consider the reflected wave, when we have to consider the reflected wave, and if the reflected wave is present, then what is the significance of it, and when the reflected coefficient reflected wave is 0, what is the significance of it, and if the reflected wave is linearly polarized, what it shows. So that all you have to very much clear, then only you will be able to solve equations from the topic of parallel polarization.